Thing we have to talk about today for this next test is really how is carbon dioxide transported, first off, and then second, how we regulate when we take a breath and when we don't. So really with carbon dioxide, we're going to see carbon dioxide, unlike oxygen, oxygen is almost entirely carried on hemoglobin. We're going to see with carbon dioxide, there's actually 3 different mechanisms that are all carrying a decent amount of carbon dioxide. The simplest one is it just dissolves into the water in the plasma, much like carbon dioxide can dissolve into the water in a soda bottle. Obviously not as much as there is in a soda bottle, but if you start looking at this, dissolved CO2 is about 7% of that. We were already kind of talking about how CO2 can also bind to the globin portion of hemoglobin, and how oxygen binding or unbinding is going to make that more simple. It makes it easier for the carbon dioxide to bind or not, that Haldane effect, so that carbamine and hemoglobin, about 23% of the carbon dioxide is going to be bound that way. The last way it's bound, and the vast majority, is about 70% binding to what is called a bicarbonate ion and acting as a blood buffer system. So we have this carbon dioxide altering this molecule that is present in the bloodstream, this bicarbonate ion, and either releasing some hydrogen ions or not, as we'll see. So this kind of shows you the carbon dioxide, when it binds with water, becomes bicarbonate, and then it's going to release those hydrogen ions, and you get that H plus HCO3. Again, this is an equilibrium reaction, so as you get more and more carbon dioxide, it's going to push it more to the right of the screen here. As you get less and less, it's going to push it the other direction, which is why when you're inhaling and exhaling, how we're going to get these exchanges taking place. And again, X is an important blood buffer, so we're not getting huge changes in the acidity of the blood based on the amount of carbon dioxide that is in there. So what this is kind of showing is gas exchange, kind of looking at the alveoli to the bloodstream. You can see at the alveoli, we're going to have, because it's a higher partial pressure in the bloodstream, we're going to have CO2 leaving that dissolved plasma to head into the alveoli. We are going to have bicarbonate ion moving, because there's less CO2 here, moving in this direction to actually release CO2 and get it to the alveolus. A little bit of that also in the red blood cells, doing that bicarbonate ion moving out, as well as the carbamine and hemoglobin moving that direction. We know oxygen, higher partial pressure here, it's going to be coming binding to this, which also helps to push these things in this direction, and that very little bit dissolved in the blood plasma. In order to keep the charge of these things consistent, we are going to have this chloride shift happening as well. Not a big deal, not something I'm going to ask about. When it gets to the tissues, you're going to see, because those partial pressures are opposite, we're going to have all these things going in the opposite direction. So CO2 coming from these tissue fluids into the bloodstream, dissolving in the plasma. CO2 going through that bicarbonate ion with that carbonic anhydrase reaction, moving into the bloodstream, binding and becoming bicarbonate ion. Same thing happening in the blood cells, and CO2 going to that carbamine and hemoglobin, because partial pressure is much higher of oxygen in the bloodstream than it is in the tissues. Oxygen is going to leave from that hemoglobin and head in, and the little bit that is dissolved in the plasma is also going to head into the tissues. So you can see how this is changing based on where we're at and what the partial pressures would be. When it comes to actually regulating breathing, we're going to see that this involves, and we already kind of know this a little bit, but we talked a little bit about with the medulla and what was going on there at the beginning of the semester. We know there within the medulla is a couple different, within the medulla and the brainstem in general, there's a couple different nuclei in there that are responsible for regulating breathing. So we have what are called the medullary respiratory center, as well as the pontine respiratory center, sometimes also known as the pneumotaxic center in the pons. So this is kind of showing you those regions where they're at in the pons on the right and the medulla on the left. So under quiet breathing, it's really going to be a couple different centers within the medulla. You have the ventral respiratory group, Again, both inspiration and expiration. The dorsal group is going to initiate these ones and relay it to the ventral group, which is going to again be involved in that normal quiet breathing, that tidal breathing, that stuff you do a lot of times without thinking. There's going to be axons from this that travel down from the upper part of the spinal cord, those phrenic nerves and the intercostal nerves that are going to innervate those muscles that are going to be involved with this. And when those inspiratory neurons in the ventral group initiate an action potential, that's going to cause the diaphragm and the intercostal is going to contract and help us take that breath in. This is going to be inhibited by those expiratory neurons, which are going to stop that and then let us exhale. The pontine respiratory center, again, in the pons, it helps to regulate that transition, that smooth transition from inspiration to expiration. If this area is damaged, it really kind of gets really erratic in terms of that breath in, breath out. This is also going to play some influence with higher order centers in terms of breathing around speech. Our average breathing rate, like I said, is about 20 to 15 times a minute. Apnea is this absence of breathing. We can do this voluntarily, so we do it a little bit when we're swallowing, or if you go and hold your breath. That is apnea. Again, sometimes can be induced by other things, such as drugs, neurologic diseases. Some people have issues with sleep apnea and their palates, and sometimes leads to them holding their breath. Can lead to major issues with sleep due to the fact that it will cause you to kind of drop out of deep sleep or REM sleep in order to take a breath in. It can lead to people being very tired throughout the day because they are getting woken up on the order of hundreds of times throughout the night without realizing it. Again, what's going to regulate is how often we breathe and how deep we breathe is going to be really a combination of a number of things, but it has a lot to do with chemoreceptors. Again, proprioceptors and a few other things, irritant and stress receptors will play a role, but the biggest thing here is going to be chemoreceptors. Sensory impulses are sent from these chemoreceptors and proprioceptors, stress receptors, irritant receptors, to those dorsal and ventral respiratory groups of the medulla, and these are going to help to alter when we breathe in and when we breathe out. Again, we can stimulate other muscles to get involved, other accessory muscles like we talked about of that forced breathing if we need to increase that respiratory depth or speed, honestly, as well. So a lot of times what we're looking at here is these chemoreceptors in the central and peripheral regions here. And these are going to be looking at generally respiratory gases in the blood and spinal cord, as well as acidity levels. So looking at the concentration of hydrogen ions or acidity. The central chemoreceptors are looking at cerebral pH changes in the cerebrospinal fluid by changes in that partial pressure of carbon dioxide. As we get more carbon dioxide, we're going to have more in the cerebrospinal fluid. It's going to cause a drop in pH. This is being looked at by these chemoreceptors. And if we start seeing higher concentrations of CO2, we are going to actually increase our breathing rate and depth. Again, as additional carbon dioxide is expelled, that pH is going to come back up, return it to a normal level, and we will go back to that normal breathing rate. The peripheral chemoreceptors look at these ones in the carotid bodies and aortic arch. Again, going to be sending messages back up through some of those cranial nerves, either the glossopharyngeal or the vagus. I'm not so worried that you know one of those is which or whatever. But again, these are going to go up to those respiratory centers and can, depending on what's going on with those blood pHs and respiratory gases, can either increase or decrease breathing rate. And again, mainly stimulated by changes in hydrogen ion concentrations due to changes in that partial pressure of carbon dioxide. Increased partial pressure increases hydrogen ion concentration, which is going to increase acidity, which will lead to changes in breathing rate. And what's kind of interesting is it's not always even just the carbon dioxide. If due to changes in like what the kidney's doing, you will also sometimes, if your blood gets increased acidity, increased hydrogen ions, even if it's not due to respiratory reasons, you will actually increase your breathing rate and depth to try to deal with that. we're going to see sometimes these can also be stimulated by changes in blood partial pressure of oxygen issues. Generally, changes in the partial pressure of oxygen will make it much more sensitive to CO2 changes. What we're going to see is you have to have very large changes in that oxygen level, arterial oxygen levels, to really start stimulating these chemoreceptors all on their own. This can happen sometimes, though. So especially with folks that have really kind of chronic pulmonary issues, so COPD issues. What happens a lot of times if you have really bad emphysema, your CO2 levels are always going to be high. Your acidity levels are always going to be a little bit higher than they would be normally. What can happen on these ones is you can get some dysregulation due to breathing rate and depth because of those partial pressure of carbon dioxide. The body, again, stops using that as the main stimulus. Like I said, normally for most people, we are CO2 dependent. Why you take a breath in when you do is because CO2 levels get too high, not because oxygen levels are too low. So generally, if you have to take a breath in, it's because your CO2 levels are getting too high and it causes you to take a breath in. If that was the case, if it was based on oxygen levels, you wouldn't be able to hold your breath nearly as long. What can happen sometimes, though, is with respiratory disorders, you lose the ability to get rid of enough carbon dioxide, and that becomes dysregulated. So what those people start depending on is oxygen levels. The oxygen levels actually become their drive to breathe, and this is what we refer to as hypoxic drive. These chemoreceptors for oxygen start being the ones that really regulate it because the CO2 has become dysregulated. Because the carbon dioxide levels have got so long, the chemoreceptors get less and less sensitive to them, and by default then this O2 levels start regulating this. This is why it can be very dangerous to give somebody that has emphysema or a COPD issue 100% oxygen. You can actually interfere with, especially if they're unconscious, their drive to breathe. And because they're getting enough oxygen and stimulating those chemoreceptors, they actually lose their drive to breathe on that sometimes. So again, normally under this, neuronal control of breathing is really, like I said, a CO2-based system. Increases in partial pressures of carbon dioxide lead to decreased pH in cerebrospinal fluid, and the central chemoreceptors here stimulate those medullary centers. About 70% is with that. About 30% is from the aortic and carotid bodies. Seeing the changes in CO2 levels, those will also influence the medullary center. When these get high enough, those CO2 levels, it's going to stimulate those respiratory muscles to contract, increase the breathing rate and depth, which again is going to bring those CO2 levels and pH levels back to normal. Other things that can influence this are different proprioceptors. As you start moving your body and muscles around, increased movement is going to kind of signal to the body that we're going to have an increased need for oxygen. And just like with cardiac output going up, breathing rate and depth tend to go up with this as well. Baroreceptors can also play a role in this. You can really, as you start getting too much air, the lungs, as you're breathing in, there is a reflex here to prevent the lungs from getting overstretched, and that will actually stop the body from inhaling or having those muscles go any further. So baroreceptors can be inhibitory of that. Again, sneezing and coughing a lot of times are two of these weird irritant receptors that they can cause these very large, kind of seal the glottis for a second and then do a very explosive force to try to clear the airway. So when you think about a cough, your vocal cords and that stay closed, the epiglottis stays closed for a second. We build up a lot of pressure and then let it off really quick, like a release valve to try to blast this whatever's there. So with the sneeze, the soft palate closes down, doesn't seal the nasopharynx, it goes out the nose. With a cough, we seal the soft palate, send it out the mouth. Again, either of those trying to clear that airway. Other things that happen in the hypothalamus, if your body's getting warm, a lot of times what you'll do is you'll breathe more often to try to cool that. Again, our bigger thing is sweat in that, but like other animals, we can actually drop body temperature a little bit through increased breathing rate. Again, I think everybody's aware, emotion, stress can lead to changes in the breathing rate. And again, obviously, in order to do speaking, we have to influence this with the primary motor cortex and that as well to actually regulate our breathing when we're actually speaking. And it's going to bypass some of those with our breathing patterns that we normally do when you're actually speaking. It kind of overrides that, and you are actually going to be much more conscious of when you're breathing in, when you're exhaling. So again, a lot of these respiratory structures in terms of the smooth muscles and glands, those different nuclei are going to be doing that. Lead to vasoconstriction, vasodilation with the autonomic nervous system. So the vagus nerve is going to be highly involved in parasympathetic, and some of those thoracic exits going to be going through the respiratory plexus to some of these structures here in this smooth muscle. Again, controlled by the brain stem. Breathing muscles, composed of skeletal muscles, as well as really composed of skeletal muscles, brain stem nuclei, and that are going to control it when you're not paying attention. A lot of times the higher order brain regions can override that to a point. So with speaking, we kind of override that breathe in and breathe out around what we're trying to do there. The other thing is you can voluntarily try to hold your breath, but at some point or another, those nuclei will take over and force you to take a breath in as CO2 levels get too high and you start getting hypoxic. So, like I said, we have some ability with our higher order brain regions to override some of those brainstem functions to a point. So the respiratory centers normally, like I said, doing the normal breathing, that rhythmic input and output here through the phrenic and intercostal nerves to regulate the breathing rate. Like I said, cerebral cortex can consciously do this and stimulate the breathing muscles. Again, can override it to a point, but sooner or later, if you try to override it too much, those involuntary things will take over and force you to take a breath, which is part of the reason people drowned. A lot of times if you're underwater too long, sooner or later, your drive to take a breath in will actually overtake that and you inhale water, for example. Again, other things can do this as well. Like I said, those chemoreceptors, we talked about that. Pain generally will inhibit breathing. If your face hits water, it does tend to give you an apnea thing. A lot of times, and you can actually see this with babies, a blast of air to the face will have a tendency to actually trigger an apnea response. Like I said, babies, this is very involuntary. If you've ever been around little infants, if you blow a little bit in their face, they will actually they will stop breathing for a second. The other thing that's kind of interesting is we can, based on our breathing, influence these kind of the chemistry that's taking place in the blood supply. So if you were to hold your breath, what's going to happen? CO2 is going to build up, oxygen is going to drop, going to increase the acidity. And generally, after you stop holding your breath, you're going to have to try to breathe more often. Other things that happen if you hyperventilate, so a breathing rate and depth that is well beyond the body's demand, it will actually increase PO2 levels, decrease CO2 levels. We talked about this a little bit before, but it can actually lead to vasoconstriction, go into the brain and cause you to pass out. Again, what's kind of interesting about this one is if you pass out from this, you'll stop breathing for about 45 seconds, and then when CO2 levels get high enough, you'll take a breath in. I've actually worked with different people that worked as EMTs, and they said it was always the freakiest thing when somebody passed out from hyperventilating because they wouldn't breathe, and you're starting to get worried that they're not going to take a breath in, and then after about 45 seconds to a minute, they take a breath in and then generally come back conscious slightly thereafter. Again, these levels of this, will play around with this. Normally at sea level, you're not going to get way more oxygen in there, but this is also part of the reason if you ever wanted to, let's say, beat somebody in a breath holding contest, if you hyperventilate and then hold your breath, you will actually be able to hold your breath longer because you've got rid of a lot of CO2. You're technically not getting hardly any more oxygen in there if you're at sea level for the very simple reason your hemoglobin's basically saturated at sea level, but you are blowing off a bunch more CO2. So if you're ever really wanting to beat somebody and take some money from somebody, if you hyperventilate for about a minute, you generally can almost double the amount of time you can hold your breath. And levels of CO2 below normal is what we refer to as hypocapnia. So blood, like it says there, low blood CO2 levels cause a vasoconstriction, which is part of the reason sometimes if you hyperventilate, you do pass out. And a lot of times we've talked about this as being respiratory alkalosis or acidosis. Again, because one of the quickest ways to get rid of acidity in the blood is to increase your breathing rate and depth. We're going to see that breathing is one of your biggest blood pH regulators, physiologic regulators. We'll talk a little bit about the kidney later on too. It can excrete ions, either hydrogen ions or bicarbonate ions to change blood pH. But your breathing is actually your biggest regulator of blood pH. So if your blood starts to get more acidic, you are going to try to compensate for that by increasing breathing rate and depth. If it gets more alkaline, you're going to decrease breathing rate and depth. And like I said, hyperventilation, like I said, you do too much, can get you dizzy, can get you to pass out. Hypoventilation, again, working the opposite way here. Oxygen levels are going to drop, carbon dioxide levels are going to go up, and you would get an increase in blood PCO2 levels, or partial pressure of carbon dioxide, and a decrease in oxygen partial pressures, so that hypoxia with hypercapnia. And again, if you stop breathing for a little bit and then you start again, your breathing rate and depth are probably going to be increased after you've not been breathing for a little bit. Again, if you do that for too long, you're going to get a decrease of oxygen delivery, can lead to loss of consciousness, can lead to death, obviously, if you don't breathe for long enough. And again, usually leads to an increase in acidity in the blood, what we refer to as respiratory acidosis. Like I said, normally during exercise, breathing rate and depth are going to increase. So a lot of times early on, breathing depth will increase while breathing rate remains the same. If you increase this more and more, you will get an increase of rate and depth, along with an increase in cardiac output to deliver this. Again, if you end up taking my course, you'll see my exercise course. You'll see that you get early on changes and then later on changes with that. Early on, to a point, you're going to see these little kind of inflection points in breathing rate and depth as you start increasing demands on the respiratory system. Sometimes you will start increasing your breathing rate and even sometimes your cardiac output, also in anticipation that you're going to exercise. As we age, again, we're going to see a lot of times lung capacity decreases because of elasticity decreases. So as you age, you're a lot of times by about age 70, you're going to see a decrease in that ventilation capacity. Again, as we start talking about COVID as well, this is part of the reason that the folks that are older are having more issues, is partly because overall the lung capacity is decreased. The other thing that happens with this one is there's pneumonia effects. You're getting more fluid in the lungs, which increases that diffusion distance, which is going to drop your actual ability to exchange gases, and your pulse ox is going to drop as you start getting fluids in there. And then the fact you can't exchange as much air is going to decrease that ability even more. And this just kind of shows a little thing here about smoking and all the things it does to that respiratory system that inhibits that stuff. So if you want to take a look at this one, you can. Other than that, I believe this is it. This will be the last stuff that's on your next test. So after this, I will start putting in some new stuff there, and we will move on to the digestive system.